Hello, everybody. I chose the QuickSelect algorithm to cover in my presentation, and uh, before we really get going, I just listed out a few little interesting aspects of the algorithm, which is it's similar to the quicksort algorithm. I mean, the name itself is very similar, so similar to quicksort. It's a selection algorithm, so it's not necessarily a sorting algorithm, but it's a selection algorithm. And it does utilize partitioning, which we'll go into here in a bit. So just, nice little fun facts of the algorithm before we get going. High level, what our agenda looks like is just a quick introduction. Uh, what exactly is QuickSelect, and what is, and then kind of touch on its time complexity, of course. Go into partitioning, which is a big aspect of the algorithm. Um, the actual QuickSelect function, right? The actual algorithm, which we'll go into. We'll look at some code. Um, we'll look at the differences between that and the actual quicksort, which again sound very similar, but are two very different algorithms. And then I'll walk through somewhat of an example, right? I think it's important that, we kind of walk through how it actually happens or how it actually works, right? As it processes an array. It's very simple, very high level, but I think it's a good opportunity for us to kind of really summarize or um, look at how the actual algorithm applies when we're actually manipulating or processing an array. Going into our introduction. So the purpose of this presentation is to provide, just an explanation of the QuickSelect algorithm and kind of how it works, right? The scope is for this presentation is just an entry-level description of the algorithm, right? Algorithm is pretty straightforward. However, just for the purposes of this presentation, is just going to be a quick overview. Um, I like to put in some evaluation or pass-fail criteria, as we kind of call it sometimes, in all my presentations, similar to some of my previous courses. So what I did here is I just listed that evaluation criteria on the left here, so we could all, kind of remind ourselves what we look for as we kind of, as the viewers of or the audience of this presentation, have that in mind as we kind of walk through this, right? So I always like to start my introductions that way. I think it's a good way to kind of walk people through the presentation, right? So keep it going. So what is QuickSelect? Well, so it's an optimized algorithm to find the kth smallest element in an unordered list, right, or an array. So um, essentially, if we need to process an array that's however long, n minus 1 long, and we're looking for a specific element that's 20th, the 20th, the seconds, second from the last, I mean, whatnot. We could use this algorithm to search for that element, right, in an unordered list. So as we pass an array into the algorithm is, or the actual array doesn't necessarily have to be sorted, right, because the algorithm itself will actually handle that, right? Um, and what's interesting about the QuickSelect, again, similar to QuickSort, which we'll go into, is that it uses a decrease and conquer strategy rather than just a linear search, which again leads to improved time complexity, which we'll go into here in a little bit. But that's the moral of the story, right, with QuickSelect. And I try to illustrate that here really simply, right, by saying, look, again, just understanding the concept of to decrease and conquer a problem, right? We try to unpack that problem into smaller problems, which are more manageable, or that we already have information to solve, right? So once so essentially just breaking down um, the problem into smaller sub-problems, right? And that's literally the uh, the beauty of the algorithm, right? As we'll see here in a little bit, as it partitions the array into the appropriate sections, we're essentially breaking that that problem down to a smaller, more manageable problem. Um, so that's essentially, again, just a high-level philosophy, or the overall strategy of the algorithm is the decrease and conquer strategy, right? So Going into the next slide. Time complexity, right? So similar to quicksort, QuickSelect uses partitioning to help pre-sort the lists. So in the average case, right, the time complexity could be about 2n or just less than 2n, which just from a big O, notation standpoint, it would be O n, and this is average, right? An average scenario. However, there are always the worst case scenarios where the element that you're looking for is probably at the very end of the array, and so it would have to process all those or evaluate all those elements as it scans through the array. So there's always the worst case scenario, and that performance, that time complexity performance could be quadratic, right, which would be n squared. But on average, and this is why this algorithm is quite popular, is the fact that it's n time complexity, right? So moving on, partitioning. Okay, so again, this is actually one of the big strengths behind the algorithm, is how it partitions, right? Um, Basically, so QuickSelect utilizes the Lomoto partitioning or partition algorithm, which typically uses the last element. I mean, technically you could tell it to choose whichever one, the first one, middle one, but generally what I've seen and from what I'm reading, it usually uses the last element in the array as the pivot, and then essentially scans the array starting at the very beginning or the low, as we'll see here in a little bit in the code. And moves the elements around the pivot appropriately, right? So let's go into the code real quick. So we declare the actual method partition. The arguments are the array and the low and high indexes, right? And the first thing it does is it defines or declares the pivot to be at the very end. So again, the last element. And then it declares the pivot location or the starting location, which is at the very beginning, or low, as we call it. And then it goes through the for loop. And as it goes through the for loop, it essentially evaluates the current index with the pivot value, right? The pivot element value. So if it's the last element, it's going to look at the value and it's going to evaluate, or it's going to basically check if it's less than, right? And if it is, it's going to try to move it to the other side of the pivot, right, or the pivot location. So what it's going to do is it's going to store that current index value into a temp variable. Then it's going to move the pivot location over to the current index, right? So basically move it around it. And then it's going to then put the temp variable back into the pivot location. And that's what we see here, right? The array at the pivot location is going to equal the temp variable. And then at that point it increments, right? So essentially it's shifting these elements around the pivot. Once it's complete scanning the array, it's going to finally swap the actual pivot element into the pivot location. And that's what we see here at the very end, right? We're saying, okay, store that element into the temp variable, then move your pivot location to where that one used to be, and then put the temp variable back into the pivot location. So essentially it's swapping it in. And then it returns that location, right? So when you call this partition method, you should expect to get an integer, right, which is essentially the index of the pivot location. So that might be wherever that value is relative to the other values, right? So that's how this partition method works, right? So now going into the specifics of the QuickSelect code, it initially calls the partition method just like we described, right? So up here, where's my little laser? Do I have a laser? There it is. Yeah, so we declare the method. I'm sorry, yeah, the QuickSelect algorithm, the method. We pass again the array, the low and high, and also the k argument, right? Which is basically what element are we looking for? We're looking for the first one, second one, third one, whatnot. So we need to all, obviously call that. But the first thing it does is it finds a partition. So it's going to say, hey, go ahead and let's start partitioning. And knowing what we know about the partition algorithm now, it's going to use the last variable as a pivot. Um, and so what this quick select algorithm does is it creates basically a in scope variable called partition. It calls a partition. So partition will now hold the location index of the pivot, right? Um, and then we're going to evaluate that. We're going to say, okay, so now we have this index, right? Does that equal k minus 1, right? So is that the one we're looking for? If it is, great, return it. If not, then if this is where we need to evaluate, okay, if we found it, if it's the actual element we're looking for, if it's the second or third element, whatever, which one it is, then return it. If not, then is the partition less than or greater than the pivot value or the k value, right? The argument, right? The one that we're looking for. If it's less than, then recursively call yourself again, right? It's going to call itself again, quick select. However, it's going to use the new values, or essentially it's going to focus. Well, it's going to go down the appropriate partitions, right? So if it's less than, then the k value, right, that we're looking for, then it's going to go down that path. If it's greater than, then it's going to go down the other path. And I'll talk about how, that's what essentially differentiates, the quick select uh, than the quick sort, right? But that's exactly what's going on here, right? Saying, hey, if it's less than, then recursively call yourself again um, and go down this side or that side, right? And it's going to continue to do that until the partition or the index of the pivot equals the value that we're looking for, right? So that's in a nutshell how it works. Um, so, so yeah, that's the code. Pretty simple, pretty elegant, but that's how it works. And then the quicksort difference, right? So the quicksort is a divide and conquer, right? It's really a totally different algorithm, right? Um, but it kind of uses the same methods, right? It uses obviously the partition, but quicksort continues to go down both sides of the pivot, right? Because its whole goal is to sort the array, not necessarily, looking for not necessarily a selection, right? It's looking at sorting, so it's going to go both sides. Um, Quick select evaluates the pivot location and again only goes down the appropriate path to find the actual element that we're looking for. It doesn't go down both. And that's again the biggest difference between the quick sort and the quick select. So anyways, I felt like it was important that we describe the differences just because they're so similar, right? But okay. Okay, yes. Okay, so now we're at the example, and I think this is great again because it's a very simple example, but I think it'll really demonstrate how this algorithm works. And so yeah, let's get started. So so here's just an array, right? And we're going to go ahead and uh, pass this into the quick select algorithm, and we're looking for this fifth smallest element, right? That's what we have here, right? We're looking for the fifth one. So just like we understand now, the first thing it's going to do, it's going to partition the array, right? And again, just like we already know, like we just went over, um, it's going to use the last element as the pivot. So it's going to partition, and it's going to move the elements to the appropriate sides of the pivot, and then it's going to return the pivot location. So for now, it's the second index, right? So it's definitely not the fifth smallest. It's like the third smallest. So again, understanding the algorithm, it's going to recursively call itself again. However, this time around, it's during the quick select um, evaluation, it's going to choose the right side, right? Because we're at the currently right now the pivot's at the third location, but we're looking for the fifth smallest, so it's going to be on the right side. So it's greater than. So again, it's going to choose the right side, and it's going to recursively call itself. And again, just like we know, it's going to partition the array, the subarray now, right? Only that sub portion of it. And again, just like we know, it's going to use the last index, which is 10. Um, and it's going to return now the new index for the pivot. And as we could see here, it's 5, right? And that's actually the one. And if you recall the element or the algorithm, it's going to evaluate the pivot location with the k value or the element that we're looking for, which again is 5. So the algorithm completes. And that's pretty much how the quick select algorithm works. Pretty straightforward, but quite elegant at the same time. So that's quick select.